Okay, hello everyone. Welcome to the DP1 session. So this session is going to be focused on Data Preview 1 and how you can access it and what is contained in the data preview. This session is going to be I guess we'll start with some reminders. So you probably have all seen these slides already in the various sessions you've been at. We have a code of conduct here at the RCW, and so you can get more information about that here. We want professional conduct, and please reach out if you experience something. Oh, wait a second, let me get rid of this. All right. Okay. All right, so just going through these reminders, it is still the era of COVID-19, so please be courteous of other people's comfort zones. There's a lost and found at the RCW registration desk, and also please be conscious of your colleagues' social batteries. All right, so just some other reminders. We are broadcasting on Zoom. There are many participants on Zoom, so please, virtual participants, stay muted when you're not speaking. We are going to have somebody monitoring the Zoom chat and also the Slack chat for questions, so feel free to type those in. We request if you have a question, please wait for the microphone to arrive to you so that people on Zoom can hear your questions. We have a Slack channel for this session, so please feel free to join that. And yeah, please feel free also to raise your hand if you'd like to ask a question. All right, so this session is about Data Preview 1. So this is the most recent data release that's been that came out about a month ago. All of the speakers in this session are from the Rubin Community Science team. So we are a team that is charged with helping the research community to train and prepare for doing amazing science with Rubin LSST. So these are all of our members. Many of us are here at this meeting, so please feel free to ask us questions. 5 of us are going to be giving little presentations in this session, so we'll introduce them as they come up. This is the agenda for this session. So we're going to start with a brief overview of getting started with the Rubin Science Platform. So this is sort of very basic. How do you get started? What is the Rubin Science Platform, and how do you use it? We're then going to have a Data Preview 1 overview session presented by Andres Plazas Malagon. Then we're going to go into some smaller sessions about the specific data products that are contained in Data Preview 1. So we're going to talk about visit images and source tables by Gloria. We're going to talk about, I'm going to talk about deep coad images and object tables. Sorry, I didn't introduce myself. My name is Christina Williams. And then we're going to hear about difference images and catalogs from Jeff Carlin. And then we're going to talk about solar system data products by Sarah Greenstreet. All right, so I'm going to get started with an overview of the Rubin Science Platform. All right, so the Rubin Science Platform is an online venue for accessing the Rubin data products. And the Rubin dataset, of course, is very large, and so you can't just download it to your own machine. So the Rubin Science Platform provides a next to the data venue for doing all of your analysis. And it is also consists of a set of integrated web-based applications that help you do analysis with Rubin data, and also access the data, do visualization. And we have all of these great LSST software packages that are ready for people to use for their own analysis. So the Rubin Science Platform consists of 3 different ways to access the data. So today we're going to talk about the portal aspect and the notebook aspect. The portal aspect is a great place to do exploratory analysis with quick visualization infrastructure. And then the notebook aspect is a place where you can build sort of more reproducible analysis tools, like with Python notebooks, or run code and access the Rubin Science the LSST pipelines, science pipelines packages. All right, so this is the landing page. The location of the Rubin Science Platform is data.lsst.cloud. You need an account to access it, but we have online instructions. We're not going to go over that today, but there's online instructions on how to get your account set up. Once you have an account, you can go to this landing page and access the portal aspect or the notebook aspect from these big buttons. So the portal aspect is a great way to do exploratory visualization of the data products. So we have some very basic user guides available online to get you started if you've never used the portal aspect before. So you can go to rsp.lsst.io/guide/portal to find out more information. So here's a screenshot of the landing page where you can see some of the resources that we have available for you and some of the explanation that can guide you through getting started with the portal aspect. So we also have built, the community science team has built a number of portal tutorials that allow you to access Data Preview 1. So we have those portal tutorials available at dp1.lsst.io. And here you can kind of see just an overview of some of the things that are available. We have tutorials that help you explore how to use certain functionalities of the portal aspect and how to access certain data products from the DP1 data repository. So I encourage you to go to this website and sort of play around and see how to do some of these sort of first look analyses with the portal. So the portal is also, it's sort of a graphical user interface that allows you to explore the data without necessarily using any coding language. So there are the services that are provided there. We have table access protocols, and a number of other IVOA, International Virtual Observatory standard services that you may be familiar with from other observatories. And these allow you to browse the data sets, do queries for catalog objects of certain types that you set the criteria for, to find, retrieve, and display both catalogs and images. And then you can also create interactive plots using what you have retrieved from the Rubin data. So this is a very exciting aspect that I hope you will explore after seeing this presentation. All right, so the notebook aspect is sort of a more programmatic access to the data. So there's a command line with a bunch of Python infrastructure, and there's also a JupyterLab notebook environment where you can code your own analysis packages and tools and things, and you can also bring your own analysis tools that you've been using on your own machine and bring them onto the notebook aspect to use with the Rubin Science platform. So all users have their own account that with 35 gigabytes of storage and a certain amount of memory. And so you can, there's a number of things you can do there with the notebook aspect and running Python scripts and using command line access. And also you can use the LSST Science pipeline infrastructure. There's a lot of packages there that are built already to use the Rubin data format. So this is the landing page of the notebook aspect, and so that will also guide you to how to get started with the notebook aspect. All right, so one last note about the Rubin Science platform, and a great place to get help as you start to learn to use DP1 and the Rubin Science platform is the Rubin Community Forum. So this website is community.lsst.org. This is a great place to get support for things, get questions answered. We aim to get questions answered on a very timely basis. And so it's also a great place to search for questions that have been previously asked, which may already give you answers to some of your questions. So I definitely encourage you to go ask your questions at the Rubin Community Forum. All right, so now we're gonna maybe pause for questions about the Rubin Science platform briefly before moving on to Data Preview 1.
Notebook interface that you mentioned, is it persistent in the sense if I pip install something, will it stay there like later? And kind of relate to questions, if I screw something and I pip installing it, can I kind of reset it back to something like a clean slate type of thing?
Yeah, so you have your own disk space there. So if you write analysis code and build tools, then they will stay there up to the limit of the user capacity, I guess, for the memory on that. I think there's also some other, maybe somebody here has better idea or can speak to Yeah, Greg, do you want to say
Yeah, there is you can install packages in the notebook environment, and there is a mechanism for resetting to like an initial condition. So yeah, those are definitely possible.
Thank you so much. I was kind of curious if, let's say something that we're doing is more than the 35 gigs. How does one like go about like acquiring more space? I'm assuming like you would have to like buy it or something, and there would have to be some sort of communication involved, but I'm really naive to that.
Yeah, so my understanding is there is an avenue for requesting additional disk space. I'm not sure that the details have been, he's gonna answer that. Okay, great.
Hi, this is Adam Thornton. I'm on Square. I work on the science platform. So in general, if it's temporary space, put it in the directory pointed to by your environment variable scratchster, but it will get cleaned up every Sunday morning. If you need much more space than that, then yes, talk to us. And I'm not sure where us goes between Square and CST yet, where it's kind of a work in progress. We have the Rubin partition, which can be used for defined collaborations. But in general, if you find that you need a lot more than 35 gigs of permanent space, the RSP is probably not the place you should be doing that set of calculations. You know, the USDF based batch system might be a better fit for you. But if it is purely collecting intermediate results, like that's what your scratch space is for, unquoted but temporary.
Yes, hi. Thank you for the presentation. I've used RSP for basic queries and other simple exercises. But I have a question. Does the RSP include a suite of tools associated with tapping into the alert stream and doing DIA? Or is that a different set of tools somewhere else?
So you mean receiving alerts from?
Yes.
I'm not that familiar actually with the alert stream, but maybe somebody who, oh, you're the next question. Okay. Maybe someone from.
So in its current state for DP1, that capability doesn't exist in the RSP, right? The expectation is that people will subscribe to alerts through brokers that are formally independent of the project. I mean, they have a relationship with the project, but they're independent of the project. So for receiving alerts, your relationship is with the broker that you choose to partner with, not with the project. We don't send alerts to individuals. We distribute them to brokers, and brokers send them to individuals. There is going to be an alert archive that you will be able to access from the RSP. Yeah.
Eric Tollard, Space Telescope. So I have a very specific question, which is really a meta question. So the specific question is, how do you do cutouts? The much more meta question is, if I were not in this room, it's a trick question. I already looked and couldn't figure it out. But what would you recommend is the way I would find it out if I wasn't able to talk to the experts that are in the room right now?
Yes, well, we do have infrastructure for making cutouts. So there are, if you look in the notebook tutorials that are online at dp1.lsst.io, we do demonstrate how to do that in a notebook tutorial. Didn't find it. Okay.
No, it was really hard to find and it didn't work for me, but let's not worry about that second part. I'll talk to someone else about that.
Okay. Sorry, what was the second part of your question then? Or
is that the answer to how should I be telling all my colleagues who aren't going to be at this meeting how they can find that stuff out? Is it just go to data.lsst.org or cloud, whatever it is, and hope for the best?
Well, I think the tutorial is probably the best way to find information on how to do the cutouts. Gregory, do you want to add something about the cutouts? Or
At this point, I should probably identify myself. For those of you who don't know me, I'm Gregory Dubois-Felsman. I'm from Caltech, IPAC, and I'm the effectively, to use more common terminology, the science lead for the science platform. So I mean, obviously, if you found the tutorials A, hard to find, and B, not working, you tell us that and we fix them, because the tutorials are supposed to be the answer to your question, right? Yeah. I mean, there are other answers in depth to your question. If you go through the RSP's image query services, the data link responses will tell you how to make cutouts. It's there in the data. So we're trying to be good IVOA citizens, hopefully better than anybody else. That's our ambition. So that's another answer. And then, since you mentioned cutouts, it's worth saying, and this is in the CST documentation, but I'll say it out loud. Right now, the cutout service is sort of one cutout at a time. One of the things that isn't finished yet, remember this is a data preview, is a bulk cutout service. And we know that there's a tremendous amount of demand for being able to make large numbers of cutouts in a more organized way. So that'll be the topic of a future meeting.
I'll just add that if you find that notebooks are not working for some reason or another, please post on the community forum and get your, because we try to respond to these things and fix them when errors occur. So. Okay. All right. There is a question online. I don't know how we're doing on time, but maybe we can make this one the last one and take.
So this is from, do you want to speak? You can unmute and.
Oh, I can do it, Yumi. Thank you so much. Yeah, hi. Hi, I'm Charles Liu. I'm at the College of Staten Island. I have numerous student collaborators across a wide variety of institutions. None of them are power users, so we'll never hit the limits or anything, but they all are accessing it. Is it better for us to get one account that we all use together, or should we all each get them and then just each do our little tiny things like in coordination that way?
I think the answer is it's best if all of your team members get their own accounts. You must get your own accounts.
Okay, everyone gets their own accounts. Thank you. All right, just don't want to clutter up your infrastructure.
I don't know. That's fine. You don't have to worry about that. As long as they have data rights, I think it's fine.
Okay.
All right. Maybe we can move on to data preview 1. We do have a session at the end of a few minutes at the end for further follow-up questions. And of course, feel free to post them in the chat. Anyway, our next speaker is Andres Plazas Malagon talking about data preview 1.
Thank you. This is all. Thank you, Cristina. Yeah, my name is Andres Plazas Malagon, and I work for Slack National Lab, and I'm part of the community science team as well. I'm going to tell you a little bit about DP1, like a general overview. Then after that, we're going to have more detailed talks about the data products that you can find with DP1. So just wanted to say that everything that I'm going to say here, it's in the documentation, is in dp1.lsst.io. There's also a paper in preparation that we've been writing. It's in internal review, but you can go to ls.st/rtn095, Rubin Technical Note 95. There's a lot of details in there. But so the DP1 data sets is a subset of a commissioning campaign performed with the commissioning camera, the LSST ComCam. Which is like a subset of the bigger LSST cam. It has 9 CCDs, only 9 CCDs, still 144 million pixels, compared to the 189 pixel size CCDs that the LSST cam has. So this campaign was conducted at the end of last year between October and December. Yeah, so it was conducted during these 2 months. There were 7 fields that were observed, and in all the 6 filters that the LSST will have. So this was a campaign that it didn't have continuous observing, but it still was a substantial. So for this campaign, about 16,000 exposures were taken, and the DP1 set is a subset of this, of about 2,000 exposures. So in this slide, we can see the fields that were chosen for this campaign. Overall, there are about 15 square degrees, but as you can see by the location on the sky, They have different purposes, and some of them are closer to the galactic plane, to the ecliptic. Some of them are away from the galactic plane. This is a plot that you can also find in the paper draft that I mentioned, RTN 095. You can look into more detail and also compare with other LSST, the planned LSST zones that are currently there. So, but in more detail, so we have these 7 fields. And in this plot, we have the actual names and the coordinates on the sky. But these fields, we have to keep in mind, of course, that they were chosen, first of all, in order to do commissioning of the observatory. The LSST CAM instrument itself was not commissioned, but the fields were chosen, for example, to test the adaptive optic system, to test the LSST science pipelines. And in addition, also, we wanted to cover, to have a sample of the science, of science fields that would cover the science objectives that will be conducted with the LSST. So just to go briefly on each one of those fields, we have a globular cluster 47 TAC. We have a low ecliptic latitude field optimized for solar system science. We have a local dwarf spheroidal galaxy, the Forknest galaxy, and then we have 2 extragalactic fields that are optimal for extragalactic science, the extended Chandra Deep Field South and the Euclid Deep Field South. And by the name that you know that they overlap, actually, for example, with the Euclid spacecraft first data, quick data release. So this is a good or optimal for doing cross-survey comparisons. We also have a low galactic latitude field and a Seagull nebula. So you see that we have a variety of crowded stellar fields, dusty fields like the nebula. We have deep fields like the extragalactic fields, and ecliptic fields for solar system studies. In this table, we also have distribution of the number of visits per bands in each field. So here we have the concept of visit is a key concept in the LSST science pipelines, and that means 1 observation at a time per filter. And in this table, I made a little bit dry, but in general terms, it tells us that the extragalactic fields are the ones that had more observations, in particular the Chandra field. All the fields had observations in the GR and R filters. 3 of them had observations in all the 6 photometric filters for the LSST. And then again, the Chandra field being the deepest one. This is another table that shows us in a similar way, similar information about the number of epochs and the visits per epoch, or unique nights per visits, per field. And then again, we can see how the Chandra field has the most epochs, then followed by the low galactic latitude field and the Euclid Deep Field South. Then as such, they will be more suitable for example, for time domain studies. This is a plot actually taken from another document. It's called SITCOM Technical Note 149. This was a document that was produced a little bit at the end of the commissioning campaign, but it has a lot of details as well that you can look in addition to the DP1 paper that I was mentioning before. But in this plot, we have the air mass as a function of time of different epochs for a particular field, the Chandra field. So here we can see how, again, the Chandra field is the most well observed. It was observed over 21 nights over the span of 33 nights. You can see, for example, that the U and Y band images are particularly limited, but in general, it demonstrates that you can do, for example, some time domain science with this data as well. This is a table that shows us the average seen in arcseconds over all detectors from all visits per field. Keeping in mind, so the scene is good in general, but then keeping in mind, as I was saying before, that the LSST COMCAM was not itself commissioned, and for example, the active optic system was still in early testing, and that is to say that the DP1 image quality does not necessarily reflect future performance for LSST CAM, although we did get like very good nights of about like 0.6 arcseconds or so on average. But here, in general, we can see also that we still have a good scene in order to do science as well. This is one of the survey property maps. And then I should say that in a lot of, all these plots and tables that I'm showing, you can go to data.lsst.cloud and then look at the tutorials, and then there are ways in which you can reproduce these tables and plots that I'm showing. So this is a particular survey property maps, which is a depth map. It's a little bit hard to see, but the scale, the vertical scale, goes from a magnitude of 24 to 27 for all the fields. Because here in the same scale, you can see how the Chandra field, the Euclid field, and also the low galactic latitude field are the deepest ones. Another thing to notice is, for example, that hole in the Globular cluster, and then it shows us how the pipelines were being stress tested in that particular part of the sky when you have when it's very crowded, being a globular cluster. But that, of course, was on purpose again to test the pipelines and the active optic system in these conditions. So DP1 is a small preview, but it is complete. And as our lead community scientist, Melissa, said, LSST is the greatest cosmic movie ever made, and data preview is like a super short teaser trailer. So we're really hoping and very excited for people to see what they do with this data set, and to get familiarized with all the data products and the schema to be prepared for the LSST. So I'm gonna mention a little bit about the data products that were released. So we have catalogs, object catalog, source catalog, force source catalog, difference image analysis, catalogs of moving objects, and catalogs of metadata. We also have images, deep coat images, visit images, difference, template, raw, and calibration images. And we also have maps of survey property maps and browsable HIPS maps, like hierarchical progressive survey maps. So just to tell you very general about the image processing that went into producing this data. Again, you can find more details in the DP1 paper. But the first step is taking the raw images and doing instrument signature removal. And that's a really hard process, but then in the end, users, you should not be doing instrument signature removal. This is already done with the LSST science pipelines. Then after that, we get a post-ISR image or something that is after instrument signature removal. And then we do a series of calibration processes that include deriving an astrometric solution, the mapping between pixels and sky coordinates, using photometric calibration that gives us images in nanojanskins in the end, in flux units in nanojanskin. We do PSF modeling using the PSF in the full field of view software, or PIF field software. And then we end up with what we call a visit image. So here actually, I should say that on the left column, everything that is in bold are official names of data products and that you can use in order to retrieve these data products with the RSP. So after we do these sets of calibrations, we do a coaddition process in which we take the individual visit images. We do a mean stacking weighted by an inverse variance. There is a quality cut in the PSF full width of hat maximum of 1.7 arcseconds, and that gives us a deep coat image. And then in order to do transient science, we also produce a template coat image, which takes the third best seen images. That is to say, for example, if we have 36 images for a particular point of the sky, you take the 12 best images with the best seen in order to produce this template coat. We also produce difference images, doing difference image analysis, in which we subtract these template coats from the visit images, and we end up with a difference image data product or image. Then we do detection, which that means, for the purpose of DP1, it means that any object or any source with a signal to noise ratio greater than 5. We do the blending with a version of the Scarlett algorithm, which is called a Scarlett Light. It's the blended algorithm, and in the end, we keep what is called the children or the blended objects. And then after that, we proceed to do measurement of centroid, size, shape, flux measurement. We also do force photometry, in which, by definition, we do measurements made at fixed coordinates, and then it could be, of course, sub-threshold or less than the signal-to-noise ratio of 5 because of the definition of force photometry. And we also do moving object linking to detect objects, for example, in the solar system. In terms of the catalog descriptions, we can do a rough classification between static sky products and transient and variable products. So for the static sky, we have a source catalog, which are the measurements of the signal to noise ratio greater than 5 detections in visit images. In an analogous way, we have an object catalog in which we have multiband force photometry at the locations of all the sources and all detections in the deep coad images. And then we have also force source catalogs, which is force photometry at the locations of all objects in every visit image and in every difference image. We also produce light curves for objects. Then for transient and variable science, we have DIA source catalogs, difference image analysis source catalogs, analogous to the source catalog with objects with signal to noise ratio greater than 5 in difference images. Then we also have a DIA object catalog, the locations of associated DIA sources within a radius of 1 arcsecond. And then we have a forced source on DIA object catalog, which is force photometry at the location of all these DIA objects in every visit image and every difference image. And then we also produce light curves for DIA objects. And then I know that it's a lot of names, but again, I can assure you, if you go to the tutorials at your own pace, you're going to have one tutorial per data product, and then you can see in detail exactly what we mean. And also in the documentation, we have descriptions of all these projects. And also my colleagues are going to tell you more about this in a few minutes. When just going very briefly here, we also have, well, catalogs for moving objects. I already talked about the DIA source catalogs, but we also have data products or catalogs for solar system investigations, like the SS object catalog, which are associations of DIA sources into moving objects, the SS source catalogs. And we also have the Minor Planet Center ORB or orbital, the MPC ORB catalog, which are derived orbital parameters from the minor planet centers that are not only limited to the LSST detections. Two other sets of catalogs that are important are the ones that have observational metadata. So we have metadata at the visit level, which has metadata on individual observations, refers to full focal plane, bore side, which is where the telescope was pointing, and it gives you information such as the air mass, coordinates, dates, time per band, etc. And then we also have an analogous catalog of metadata at the CCD level, at the detector level, that has one row per detector per visit, and then has information again on air mass or PSF image quality, 0 point, and magnitude limit. Okay, at this point, maybe we can stop a little bit, or we can continue with, I don't know how much time we have. We're doing great, okay. So we can talk a little bit if you have any questions. Yeah.
Charles Liu asked, was the all ecliptic latitude field where all those first look asteroids were discovered? And Lauren actually answered, said no, the first look products were all based on the data taken with the full LSST chem. For the DP1 LSST ComChem data, I think the number of new solar system object detection is sort of order of 93.
Thank you for the question, and thank you, Lauren, for the answer. Yes.
So how did you deal with the satellite streaks and artifacts in the images, and how hard was it?
Yeah, I'm actually not involved in that particular part of the algorithm, but I believe that it was part of the outlier rejection, the usual outlier rejection process when doing the coating. We do have software that does regular, like even, like regular, like a streak correction where you find the streaks with a half transform, and then you do the correction. I don't know a lot about the details of that. I don't know if some of my colleagues know more about that, but I believe it was part of regular processing right now. I don't know the scale actually of how much in ComCam data and DP1 it was like found, but yeah, I believe this is part of, I know that this is part of the LSST Science Pipeline's regular processing. I don't think it was particularly hard, but this is me speculating. So Otherwise, I would have heard about it. I don't know if there's anybody else who can give a better answer. But if not, I can follow up with you, and I know the experts that might be here actually. Meredith Rolls at UW, for example, or Claire Sanders in the team, in the DM team.
Thank you so much. This is super informative. So I had a question because in past surveys that I've worked with, we've sometimes had like astrometric errors that resulted in like one exposure and one band getting offset, so that you had like magnitudes for objects in one band, but the other bands had no photometry for that. Is there any way that y'all are trying to like sift out astrometric errors without relying on this like lack of photometry in one band? Because it seems like that's what's going into these like moving sources. Like would that stuff get classified as like a moving source if there were some sort of astrometric error?
Yeah, I think there's two. Again, I'm not an expert in linking of moving objects, and there's like a different thing. From astrometry, I can tell you we do like a process of internal astrometry when we have multiple visits, and then we do like an internal fit in which we match the difference of the location of the same thing in different visits. It should be the same. So that's an internal astrometry. We do also like an external or absolute astrometry using Gaia. We use a fitting process that was used for the dark energy survey for the dark energy camera. I can give you more details. It's actually called GVDES, Gary Bernstein DES. That's like the fit that is used. And I have one expert here. Pierre Francois is not here. Well, anyhow, that's for the astrometry. Then for the linking, I think that's another thing. I guess we should have like a solar system expert, but that's like a different thing in order to link triplets is called, or something like that. Tracklets. Okay. So that's what I can tell you about that. Yeah.
Thank you for the presentation.
Yes.
My question is about forced photometry. We hear that term a lot, and in general terms, it means I know where the object should be, and I go and measure at that location. But in detail, does that mean that you know that position extremely well and you don't allow it to move when you do the forced photometry? Or
yes,
is it somewhat different from that?
I believe that that's the case, yes. That you know the position, and then you go back to the single visit images and do the measurement in there. That's, yeah. I don't know if anybody wants to give more details about that. Yeah. Maybe. Yeah, he's gonna give more details.
I don't know if we have somebody else from the pipelines team here in the room who could back me up on this, but I don't know if it's fully implemented yet in the version of the software that was used for DP1, but certainly we would expect to do things like correct for DCR in where to actually apply the forced photometry, right? But it definitely assumes that it's in the position in which it was found on the COAD, right? So correct, yeah. So we don't refit the position in forced photometry, but basically by definition.
All right, are there any more questions for Andres?
Sorry, I missed exactly what happened in that exchange. So if you use the forced photometry, you then also have to correct for, what did you say, DCR?
I mean, there's a lot of like pipeline stuff implicit in what I'm trying to say. So I'm not going to try to give you like a completely in-depth answer here. We do have documentation you can look at, but we detect objects on COADs, right? And they're astrometrically calibrated. We use Gaia DR3 as our astrometric reference, right? So that we believe our astrometry is very good already. We determine positions from those detections, right? And then those positions from those detections are used on the single epoch images to perform PSF photometry or model photometry at those locations. But in terms of actually like finding those locations on the pixel grid of those images, you have to take into account instrumental effects like differential refraction, right? So that can actually put the source in a different place on the image and different filters, right? So that so that's handled by the astrometric calibration of the individual images at that point, right? So there's a sort of there are two layers to getting the right position. But the science question of like, is it assumed to be non-moving is yes. Right.
Just to keep things going, I think maybe we should move on. We have time at the end for further questions if they come up. So let's thank Andres again. And our next speaker is Gloria Fonseca Alvarez, who's going to tell us about the visit images and source tables.
Hello. So my name is Gloria Fonseca Alvarez. I am a postdoc here in Tucson at NOIR Lab, and I am also a member of the community science team, and I'll be talking about the visit images and source tables, which does include the 4 source tables. So some key concepts. First of all, what is a visit? A visit is a single observation or exposure. The properties of this visit reference like the pointing of the telescope, like Andres said. This includes air mass and coordinates. And as a reminder, LSST ComCam has 9 detectors, and each one of those detectors has the properties of those detectors, like in each visit, are called a CCD visit, and that includes properties like the seeing and 0 point. And finally, one image for a detector for one visit. After it's processed, we get what we call a visit image. You can find all the properties for all the visits in the visit table, which is accessible both via the Butler and TAP, and that includes the names for both of these data products. But you'll see here that there are 1,786 rows in this table, so that should tell you about how many visits are included in the DP1. And then we also, for all the properties of the CCD visits are in the CCD visit table, which is has 9 times more rows. Now in LSST, we use the words object and source to mean very specific things. Here, a source is an actual detection in a process visit image, whereas the object is an astrophysical object at a specific static sky coordinate. And then there are some tables. The source table contains measurements made on the objects from each individual process visit image, whereas the object table contains measurements on objects from the deep coads, which again are stacks of process visit images. And as we've heard a lot about, force photometry just means that we did a measurement at a fixed coordinate, regardless of whether or not it met a certain threshold. Usually that threshold is 5 sigma. But all of the data processing starts with image calibration. So the first thing that we do after we take an image is do instrument signature removal, and that includes bias, dark flats, and much more, so that we can correct for detector effects. We also subtract the sky background and do both astrometric and photometric calibration. So the astrometric calibration allows us to go from pixel coordinates to sky coordinates, and the photometric calibration corrects the observed flux, which allows us to actually get fluxes in units like nanojanskis. We also do PSF estimations. And after all of this data processing, we get the visit images. And again, this is 1 per detector per visit. After we have the visit images, we try to do source detection. So again, this is a detection is something that was measured with a signal to noise ratio of greater than 5 in a visit image. Some of the objects might appear blended in the images, so there's also deblending using the Scarlet Light algorithm. And here, this image just shows some example of different sources with different blendings. So some of the measurements that we get from this process are PSF, Gaussian, and aperture fluxes. Also shapes and sizes, and all of this information is found in the source table. Now, this is where it gets a bit maybe confusing. So we have, we detect sources in individual images, right? And then we stack the images and we get a deep coad. So there's force photometry in the deep coads at the locations of all those sources that were detected. But if something was, for example, not detected in an individual image, but was detected in the deep coad, since this allows us to go deeper, that also, you go back in the individual visit images and do photometry at that location. But we actually do force photometry on every visit image, but also on difference images. But you only get PSF fluxes for the force photometry, unlike the detections, which include various flux measurements. But all of this can be found in the force source table, which is a super useful table if you're interested, for example, in studying variability of objects using light curves. Now for the actual data products, the visit images here can be, like I said, accessed via Butler, simple image access, SIA, and TAP service. It is generally recommended to access images using the Butler. And as you see here, it has a specific name, visit_image. And some of the information that you will need to retrieve these images are referenced like the visit. So you could have like a visit number, the day of the observation, or a specific detector. But you can, once you go to the Butler, you can see, you know, like what is the least amount of information that you actually need to get an image. But so for each visit image, you get both pixel data and metadata. The pixel data includes, you know, the image itself with the Skype pixel data in units of nanojanskis. You also get a variance plane, which includes the uncertainty and also some masks, which, you know, for example, you know, you can see what was removed, like for example, like, you know, like a cosmic ray or something. But it also includes metadata, like information about the visit, you know, the weather, the PSF, and the world coordinate system, the WCS. Now, the source table is also accessible both via TAP and Butler. We do recommend generally to use TAP. But yeah, some of the useful columns for this table include the source ID. So each individual detection will have its own identifying name. Also includes information about the visit, like the detector, includes many types of fluxes, HSM shapes, and flags. And then lastly, we have the force source table, which again, we recommend that you access that via TAP. But for that, some of the useful columns include the object ID. You might also be, this is also includes information about like the band, what detector. It has its own set of coordinates. As you may note that the coordinates are cord_RA, which is different from the source table. And it also includes fluxes both in from the direct images and the difference images. So the difference image flux is this PSF diff flux. So if you're interested, for example, isolating some you know, variable source that might have some contaminants around it, you could look at the PSF diff flux. But one reason why you might be more interested in using this table rather than the source table, like for light curves and stuff, is because of the object ID. So all of the sources are associated by a specific object ID. So you just have to find what is the object ID for the object that I'm interested in, and you get all of the different force photometry. But if you want to get to know these data products a bit more, we do have a bunch of different tutorials. There's a tutorial on the visit images. There's tutorials on both the source table and the force source table. And there's also a bunch of tutorials that use these for more like, you know, like more science goals. But yeah, and you can find all the render versions of these tutorials at dp1.lst.io. And that was all.
All right, questions for Gloria?
Hey, thanks for that. I'm just curious, you mentioned about images use Butler instead of VO protocols, and for tables use TAP instead of Butler. Is there like some corner cases where you might want to violate that rule, or is it more like history and more standards out there than necessary?
Okay, I'll give my understanding of it, but probably other people will have to add more. So for example, if you're already looking at an image, you're looking at a specific, like a deep coad or something, like the tract and the patch, you might want to see, oh, what are the catalogs that are like for that coad, that you already have like some sort of way of referencing those data products with the Butler. You might just like stick around with the Butler. You can also find images with the TAP, but I think the Butler makes a bit more sense, just like how things are actually divided, but somebody else can correct me and add more.
All right, additional questions? We can also ask more questions at the end. Sorry. All right, let's thank Gloria again.
I think Christina's next.
All right, I'm going to give an overview of the deep coad images and the object tables that are in the DP1 data release. Okay, so Gloria talked about the visit images, which are individual visits to different patches of the sky. But over time, many visits will be accumulated over the same regions of the sky, and we combine those into what we call deep coads. Deep coad images are a stack of the imaging available in different regions of the sky with sort of the best seeing and other conditions. And in that context, we divide up the whole sky into what we call patches and tracts, which are little regions of the sky that make the imaging more digestible, and we can retrieve those deep coad images by specifying a patch and tract. So this little schematic is showing sort of a demonstration of how that looks. So for a simulated image that was in the Rubin Science platform before DP1, so but it's an example of how the real LSST survey will be divided up. So different parts of the sky are divided into patches and tracts, and you can see that these allow you to retrieve more sort of digestible parts of imaging. So we define that using the sky map, and we have some tutorials that sort of explain what that means. Each of these patches and tracts are about 2.8 square degrees in area. And then each tract is then divided into 10 by 10 patches. And so those patches are the individual images that are about 0.028 square degrees. So these deep co-added images are what we use to do static sky object detection. So this is what goes into making the object table. So Gloria was telling you about the source table, which comes from source detection on individual visit images. But the object table in that context goes much deeper, as we do source detection on these static sky images that are co-added over many visits. So to do the deep coads, we do a number of processing steps in order to do this image combination. So the co-added images are created by combining, we first do the calibrated visit images, and then we combine them in the same filter in the same region of the sky to sort of increase the sensitivity or depth of the imaging. So we pick, like I mentioned, we pick the optimal ones that have been processed and calibrated with a PSF full width half max of less than 1.7 arc seconds. We create masks, pixel masks that help to identify pixels that have been impacted by satellites or by cosmic rays, and those are excluded from the co-addition in the co-added images. We also co-register these, so we apply a alignment and warp algorithm to try to get consistent, get things onto a consistent pixel grid. And we do background subtraction, and we produce these deep coad images, which are then calibrated in units of nanojansky. So this little picture here is showing an image and an on-sky image, meaning like the science image. And then in the bottom panel, it shows you an example of some of the metadata, or not the metadata, but the other information that is included in these images. So this is a pixel mask that is showing pixels that are flagged as belonging to a source, for example, but there are many slices to these pixel masks where that allows you to identify pixels that were impacted by other things. So we also run a number of data processing steps in order to generate the object table. So object detection and its property measurements of sources that are detected in the object table. So the first thing we do is identify signal to noise ratio of greater than 5 peaks in the deep coed images. And we identify the footprint associated with each of those signal to noise greater than 5 peaks. We apply a deblending algorithm that is like Gloria said, is scarlet light, and it separates out, it tries to separate out blended objects into sort of its components so you can measure the flux of each of these individual peaks. So this is again showing an example of the scarlet light deblending algorithm where a number of objects which are very close together get separated out and their flux is assigned sort of to reconstruct the intrinsic flux of these objects. So we do this for all 6 filters. And if something is detected at signal to noise greater than 5 in any of the filters, we do forced photometry on the other filters, even if they're not detected at signal to noise greater than 5 in the other filters. So we do a number of other automated measurements on the source, or sorry, on the object table objects. So this includes measuring their flux and measuring their shapes. So there's over 1,000 columns in the object table that characterize the objects that are detected there. And so we have a number of tutorials available to sort of help you navigate all of these different columns. We provide a number of flux measurements for extended objects and also for unresolved objects, as well as shapes and sizes and other things. So we encourage you to go explore the tutorials that we have available for understanding what those columns mean. So like Gloria said, we have a number of pathways for accessing the deep coed images and also the object table parameters. So the preferred method for accessing the deep coeds is also using the Butler. So we have some tutorials available to help you understand how to do that. We also, so the criteria required to retrieve a unique image for a deep coed is slightly different than for the visit images, but we show you how to do that in some of the tutorials. But just in short, you need to specify the patch and tract that uniquely identifies the image, and then you need to identify which filter you want to retrieve. So again, you can use, to get the catalogs, you can also use the TAP service or the CIA service. Well, you can also do that for the images too, but the preferred way for getting the images is the Butler. There's also, like Andre said, is a catalog of metadata associated with the deep coed images called the ivoa.obscore table. So that some people may find that useful also. So you can retrieve the pixel data for these deep coed images, like the Science on Sky images, but there's a number of other extensions on these image files that you will get, including the variance plane, which helps you understand the uncertainty or noise from the science image, but there's also this mask plane I mentioned that flags pixel values as being associated with certain flags that are included, and so that can help with your analysis. So there's also a bunch of metadata that comes. One is importantly, a way of accessing the point spread function that is associated with that part of the sky, that part of the image from these deep coeds. So there's also information about the photometric calibration, the WCS, and also you can retrieve the number of which visit images contributed to the pixel values that you're getting out. I also want to point out that we have a schema for these catalogs that are available online here at this website, sdm-schemas.lsst.io, and that can help you navigate the very many column headers and sort of understand what's contained there. And you can also access those the information on each columns using the portal, which is another easy way to sort of understand what these columns mean. Okay, so from these deep coed images, like I mentioned, we run source detection to create the object table. You can access the object table. The preferred method is through the table access protocol. And so from there, you can run queries to search for specific objects that meet your selection criteria or within certain regions of the sky. So the name of the object table is dp1.object, and we have some demonstrations in our tutorial repository that will help you sort of see examples of how to do this. So some key columns that I want to just point out that might be of interest to people wanting to use the object table. So each object in the object table has a unique identifier, which is the object ID. There are coordinates associated with the centroid of those objects. And then we have a number of flux measurements that are available. And so they're not all widely applicable to all science applications, but there are a number of them that will that sort of meet a broad range of possible science applications that are needed. So we do, for example, unresolved PSF flux measurements, but we also model the light profiles of galaxies that are more extended using Sirsic profiles and a number of other models that can give you the total flux of galaxies, for example. So we also have some tutorials available about that. There are some other things also available, including shape measurements that help you to understand the elongation or the sort of light profile shape of galaxies and things like that. So I encourage you to go look at what is available there in the schemas for these different for the object table. Okay, so here I'm also just highlighting a few key notebooks that we've put together that demonstrate how to access and how to interpret these different measurements, specifically for deep coads and the object table. So if you have an RSP account, you can go to the main menu at the top and you will see there's a tutorials menu option where you can access DP1 tutorials, and there's a directory structure where you will find these tutorials. So there's also, if you don't have an RSP account, you can just go to dp1.lsst.io and see the rendered versions of these notebooks and see how they work. So, so yeah, I'll take any questions on this part of the DP1.
So if I understand correctly, these tracks and patches are really just a way to organize the sky into pieces. They have nothing to do with where things are observed and where the pointings actually happened.
Yes, that's right.
Okay, thank you.
I was just curious, if there are only 5 filters being used at once, how do you get the data from the melting filter?
Periodically, we swap the filters out. So over time, you shouldn't notice this difference, I don't think.
So you're waiting within the 2 months to find the missing pieces?
Sorry, I missed the last.
You're just you're waiting the 2 months until it's switched out to find the missing data?
Well, actually, the deep coads are generated once a year as a public data release. So, so I think on that time scale, you wouldn't notice the swap out of the filters.
Thank you.
Hi, do you have a repository where you have an entire field, like if we want the Euclid fields out or the Chandra fields out, where you can just take the mosaic with all the patches?
Yeah. So actually, so each of those fields is quite large compared to the size of a patch and track. So we don't have them fully assembled, but we do have some examples in our tutorial repository. I don't think we've built it for DP1 yet, but it's analogous to what we have for DP 0.2. We've produced a demonstration of how you would stitch these deep coads together if for some reason you wanted to make the huge mosaic. Sounds like Gregory wants to add something to that, though.
And just also remember the HIPS images are fully stitched, right? So there's one for each channel, and then there are a couple of color ones as well. So if you zoom all the way in, you're going to get pixel sizes that are at the native resolution on those HIPS images. So that might cover some of what you might want to do with that, at least for visualization. There's more we could say about that another time, but the monochrome HIPS maps also have FITS tiles in them, so you could even use them for aperture photometry.
So I noticed C model mags were showing up there in C model fluxes. I was just looking at the schemas and it was interesting. I didn't, then in Sloan, and, I know the answer because it's probably based on Sloan, but there's not like a clear answer to the question of exactly how is the C model mag fitted from the schemas. Is this intended? Is this somewhere where you're supposed to go look at the portal aspect or the notebook aspect and find it there? Or like how, as a random scientist, how would I find out what the C model mags actually mean as opposed to just that they're C model mags?
Yeah. So we do have, a notebook tutorial about galaxy photometry. So it does spell out there. I mean, it's not, the schema is one sentence, so you can't fit everything you need in there, but is that the question you're asking, or are you asking specifically what the C model measure? Okay, great.
I'll follow up on that a little bit too. So just first of all, this is a great opportunity for a plug. There's an RSP session tomorrow, so that you can ask some of these questions that have been being asked or maybe also relevant there. Again, this is data preview one, not everything is in place. So later on, possibly just even as an upgrade during the lifetime of DP1, but certainly later, we will have per column help information available through the portal, so that you'll be able to click on one of the 7 different flavors of fluxes that are in the object table and figure out, get to the full documentation of what that is.
Let's thank Christina again.
Hi, I'm Jeff Carlin, another member of the Rubin Community Science Team. I'm going to tell you a little bit about the difference imaging data products that are available in Data Preview 1. So first, the very basics of what difference imaging means when we use that phrase. Basically, the 3 images that you see across the top here show you the science image being, we just pointed the telescope and took a single image. The middle one, which is supposed to say template, and I just realized says tempet. The tempet image is created from a bunch of those science images that have been combined into coads. And then the difference image is created by appropriately scaling the template image and subtracting it from the science image, and what remains is anything that is changed. So this shows you an example of that. This is actual data from Data Preview 1 showing an actual supernova where that's the template image of the galaxy. You subtract that from a scaled version of that from the science image, and it reveals this supernova on the right. And so then from that, of course, you can do that for every science image that you take. And then you can create a time series of the flux measurements from all of those different images and get a light curve like this. So when we say light curve, we're just saying, flux, either in flux units or in magnitude units as a function of time. And this, again, is that actual supernova from Data Preview 1, showing you its light curve. Okay, so there are lots of concepts here. I think we've kind of touched on most of them, but the key point is you heard about the process of creating coad images. We do that same process to create the templates, but we only select the 1/3 of the images that have the best seeing. And so you get a really good high quality template image. And of course, we will do that everywhere on the sky. So we need to build up coverage in order to have a template available whenever we come and take a new visit image. Then of course, whenever we do take a visit image, we do that image subtraction, and you'll see the initials DIA quite a bit. That's difference image analysis. So otherwise, from then on, all of the data products are analogous to what you've already heard about for the static sky images. You have source tables, which come from the visit level images. So the difference image of a single visit with its template subtracted, the things you detect there are dia sources. And then of course you have dia objects, which are sort of like the superset of all of those corresponding, think of it as corresponding to the astrophysical objects on the sky. And then of course you can go to the positions where you have a dia object and then perform forced photometry on all of the existing difference images and direct images at that position. And you can use that to create light curves like the one that you saw. And in fact, we recommend, it's hidden way down here at the bottom, but we do recommend that you use forced photometry for light curves from the Rubin data products. That could be forced photometry on the science images or on the difference images, but that will give you the best quality light curves. So just to show you what the templates look like, I just created this image from one field of the Chandra Deep Field South. This is zoomed way in to like a couple arc minute scale, but this shows you on the left the deep COAD image, which contains 162 images co-added to create that. And then on the right, a COAD template that uses the best seeing 1/3 of those images as inputs. So you can see, maybe if you look at it for a little bit, you can see that the one on the left is deeper because it's used 3 times as many images, but the one on the right has better image quality because we've taken the 3rd best seeing for that template. So this is just to give you an idea of what those look like relative to each other. Okay, so a little more detail about the difference image analysis. That image subtraction process, of course, involves actually PSF matching the template image to the visit image so that you're sort of subtracting like from like image. And then so that particular algorithm, we use the Allard-Lupton algorithm for PSF matching. And then that PSF match template is what's actually subtracted, and you get a difference image. It's done on per detector, so you get 1 difference image per detector for each visit. And then we run detection. Because it's a difference image, things could have gotten brighter relative to the template or fainter. So you have to detect both positive and negative sources. So anything with signal to noise greater than 5, either positive or negative, is included in the detections. And then we run measurement of the various measurement algorithms that you've heard about to measure the fluxes of all of those dia sources. And then we associate all of the dia sources from all of the difference images using a 1 arcsecond matching radius. And the superset of all of those combined is what we call the dia objects. So you can think of it this way, in the upper right, that dot in the far right image is a dia source. It is 1 instance in a single visit image, whereas the collection of points here correspond to a dia object. These are all of the dia sources corresponding to that dia object. And yeah, and then we'll continue. Okay, so the data product type for the difference images is, clever enough, difference underscore image. It can be accessed by the visit ID, because remember, these are created from the single visit. So if you know the visit ID of the image itself, you can use that to grab the difference image. And then otherwise, this is basically the same as what you saw for the the visit images. They are calibrated fluxes in units of nanojanskis. They come with a variance plane, a mask plane, a PSF, WCS, all kinds of acronym salad comes along with all of them. And just like the source table that you heard about, the DIA source table contains the measurements from those visit level difference images. These have a unique identifier, the DIA source ID, for every DIA source. And of course, you have the coordinates, you have the time of the visit, which you need to create the light curve, of course. And you'll have the flux from the difference image, but also the flux at that same position from the direct science image. And there are other flags which are important in this case. For example, flags identifying sources that are dipoles that didn't subtract cleanly, I guess. And there's a reliability score, so you know whether this particular detection is likely to have been an artifact of some sort, or is it a reliable astronomical source. DIA object table, again, it's the superset of all of the DIA sources. Importantly, in this case, you have statistics on the number of DIA sources that correspond to each DIA object. And you have some statistics measured from the fluxes of all of the difference images and direct images. So you have some characterization of the variability of that particular DIA object, including things like, the mean flux and its min and max and sigma. There are measurements of the linear slope of the fluxes, which can be useful for identifying supernovae. There's for those who are familiar, the Stetson J index, which helps you identify periodic variable sources, flux percentiles, and various other quantities that you can use to select candidate, transient, and variable sources. Okay, and finally, there is the forced source on DIA object. And that is, as the name implies, taking the positions from the DIA object table and going and running forced measurements on the difference images and the direct images. So you get both, the last line tells you here, you get both the difference flux, meaning measured on the difference images, and the PSF flux measured on the science image. So we have various notebooks that illustrate how to work with these data products and take you through some details of how they were created that are listed here. And I will stop there and we'll move along to solar system.
Maybe one quick question because we still have one more talk and we want to be on time. Yep.
So in all, hi Jeff, thanks for the talk. In all of these processes that you're doing, you're also, realigning images and doing things like that. So my question is, when you're resampling images in order to realign them, what algorithm are you using for resampling? Is it a sync interpolation or is it something different?
I honestly don't know the answer to that.
Because it makes a difference to the photometric integrity.
Yeah, that's a good question. I'll have to get back to you.
Okay, thank you, Jeff. Feel free to find us afterwards and ask questions in community, but we're just running a little bit out of time. Sarah?
Great. Hi, everybody. I know we're getting toward the end of the session here, so bear with me as we go through the last topic here. My name is Sarah Greenstreet. I'm an astronomer at NOIRLab and also a member of the community science team. And I'll be talking about the solar system data products in DP1, specifically the catalogs for solar system. Okay, so we've gone through a lot of key concepts so far. Some of this at the top has already been discussed. Jeff just covered all of the difference image analysis, so I won't talk about that again. But for solar system, in addition to having DIA or difference image analysis sources, which are signal to noise ratio greater than 5 detections in a single difference image, we also have SS sources for signal to noise ratio greater than 5 moving object detections within single difference images as well. So once we do the difference image analysis, we get our sources. If something is detected to be moving in its position on the sky, then it is labeled as an SS source or solar system source instead of just a typical DIA source. Next, we then connect those SS sources to make tracklets. So a tracklet is defined as 2 or more detections of a single moving object taken in close succession in a single night. So we have sources, we connect them to make tracklets in a given night, and then we do additional linking to try to link those tracklets across different nights of detection. And then we have solar system objects, which are moving objects for which we have groupings of these SS sources that have been linked together. So similar concepts to some of the regular DIA sources, but specifically for moving objects. We have a lot of documentation about the processing for trying to pull these moving objects out of the images. There's 2 specific parts for the solar system processing. One is the association of previously known solar system objects with the observations that we make. So we take the observations. If we can associate it with a known solar system object, that's one piece. Anything that we can't associate with a known solar system object is then a discovery of something that had not been known before. We have a lot of documentation about how this whole process works with processing things, making tracklets, linking things together, fitting orbits to the moving objects. And so there's lots of documentation, including these 2 infographics that we put together and lots of text documentation that goes with them that you can find at dp1.lsst.io/processing as well. We have 4 tables that are related to solar system objects. Jeff already talked about the DIA source table. I'll only talk about this again here with the fact that there is this, one of the unique identifiers in the DIA source table is the SS object ID for moving object. So if an entry within the DIA source table has an SS object ID that is non-zero, so it actually has an SS object ID, that is a moving object. That's one way that you can tell that that source is for a moving solar system object. We also have the SS source table that again has this unique identifier, both the DIA source ID and the SS object ID. The SS source table has information about the heliocentric distance, positions, velocities of these moving objects, as well as the phase angles. We have the SS object table, which are these SS objects, again, are groupings of linked together SS sources. So the SS object ID is in there, as well as the number of observations that each solar system object received. And then there's this discovery submission date value as well, which is the date that the moving object was submitted to the MPC or the Minor Planet Center for objects that are newly discovered by Rubin. So for objects that are new discoveries, they will have a non-zero discovery submission date entry. If it does not have a discovery submission date, that means that it's an object that was associated with a previously known moving object in the solar system. And then we have the MPC orb table as well. So this comes from the Minor Planet Center. We download it on a daily basis and it gets looped into the pipeline. And this has the orbital parameters for all of the known solar system objects, even beyond what Rubin has found as well. So for DP1, the MPC orb table, you can see it's got just over 1.4 million rows. So this is a snapshot of all of the known solar system objects in the Minor Planet Center database as of late March of this year, as well as the known object associations that are in the DP1 catalogs and the discoveries, the solar system discoveries that were submitted to the Minor Planet Center by Rubin for DP1 as well. So the previous three tables that I mentioned, you can access both via the TAP service or the Butler. The MPC table, MPC orb table is only accessible via the TAP service. Since it's not something that's generated internal to LSST, it's not available via the Butler. There's just a quick example here if you want to go kind of explore some of these moving objects within the portal aspect of the Rubin Science platform. The top query here is an example of how you can retrieve the orbital parameters for all of the solar system objects in the DP1 catalogs. And then the one on the bottom left here is how you would change that in order to get just the solar system discoveries within DP1. And the only thing you have to do here between these two queries is in the bottom left, there's the second to bottom line here where it says where SSO.discovery submission date is greater than 0. That's how you're going to access the things that are new discoveries within the DP1 catalog. Like all of the other concepts and different data products that we have a lot of different tutorials. I've put all of the solar system related tutorials for DP1 on here. We have a tutorial for each one of these different solar system tables. We also have a tutorial that will walk you through the low ecliptic latitude target field for DP1 as well. That will allow you to kind of look at all of those, the visits, get the visit image information, as well as be able to pull out all of the solar system objects that were specifically detected in that low ecliptic latitude field, which most of them were. We also have a couple specific solar system science tutorials, one that walks you through basically what I just showed for the portal example of how you get the discoveries out for small bodies. And then another one that specifically looks at the different orbital classifications for all of the moving objects in DP1. And then there's also a notebook here for these Rubin First Look solar system object discoveries. So we had a question at the beginning of the session about these DP1 solar system discoveries and the Rubin First Look discoveries. They are two different things. So let me just talk very briefly about that because it's an important point that can easily get confusing. So with Rubin First Look, of course, all the first images from LSST were released to the public, as well as these thousands of asteroids that Jelko talked about in the session this morning with a great video that was made by the EPO team. So these Rubin First Look discoveries are different from what is in DP1. So remember that DP1 specifically has data products from LSST ComCam, while the Rubin First Look is for LSST CAM. So two different cameras. There are data products from LSST ComCam for DP1, but all we have are these images that were released from LSST CAM as part of Rubin First Look, as well as these solar system discoveries that were submitted to the Minor Planet Center. So in the DP1 preview release, there are 431 solar system objects, including 93 solar system discoveries that are available in the DP1 data set with data products all available on the Rubin Science platform. For Rubin First Look, there were 2,103 solar system objects that were submitted to the Minor Planet Center. However, there are no data products for these roughly 2,000 solar system objects currently available on the Rubin Science platform. However, all of the observations that were made by Rubin and the orbits that were fitted by the Minor Planet Center for those discoveries are available from the Minor Planet Center. It's a public data set through the Minor Planet Center, so you can actually download those observations and those orbits from the Minor Planet Center directly. And we put together a tutorial notebook There's a link here to the GitHub repo where you can find this. You can also find it on the RSP. If you go to the tutorials tab at the top of the notebook aspect, underneath the DP1 folder, there's also an MPC folder, and this notebook is in there. So it will allow you to be able to pull down all of those observations and all of those orbits for those first look discoveries, which remember are separate from the DP1 solar system objects. And with that, I'll end.
Thank you. I think we have -1 minute, so we don't have time for questions right now, but of course, feel free to approach any of us from the community science team here during the project. We have the Slack channel of the meeting, so ask your questions there or go to community.lsst.org and ask your questions that can benefit everyone. So thank you again for coming and enjoy the meeting.